So, for the third and final ICFP keynote, I'm happy to introduce Ekaterina Komendantskaya. She is a professor at Heriot-Watt University and Southampton. She studied at Moscow State University, did her PhD in University College Cork, and she has worked at INRIA and University of St. Andrews after that. Her research is about an interesting new programming paradigm called Neuro-Symbolic computing, which combines artificial intelligence and neural networks with the more traditional, the more boring programming languages that many of us work on. In this third and final keynote, she will tell us more about this paradigm and also how you can verify programs written in it.
Thank you. It works? Okay. Well, thank you so much for inviting me, because I have good news to convey you. I'm so happy to be here and deliver those good news. Let me check that my controller works. It does. So welcome, robot. The robot's name is Isaac. You might wonder why I'm showing you the robot Isaac. Well, because it's a mascot of vehicle, and you might ask, and what is vehicle? Vehicle is a programming language. It's a Haskell DSL for writing specifications for neuro-symbolic programs. You have a QR code there if you want to go and check out yourself. The important bit here, if you check out which languages are used in it, you will see Haskell as a majority of code. Then there's a bit of Coq, there's a bit of Agda in it. It will become very clear during my talk what's going on. Yeah, so the question is, okay, Isaac is mascot of vehicle, and what's vehicle? And why do you call it vehicle? And you might think it's because we're verifying lots of vehicles, old vehicles and new vehicles, but that is not the case. Vehicle is for verification condition language. And why it has to be verification condition language will become clear in a few moments. Since I'm showing you some vehicle and some people around the vehicle, there are two key people on this particular vehicle. This is Wen Koke and Matthew Duggett. They're the two main developers of vehicles, so I definitely wanted to see their faces here with me today. There are many more developers of vehicle than that. We are quite distributed. Matthew is in Australia, Wen Koke is in Glasgow. So this is only Southampton part of the group. Because I don't have a photo of everyone who develops a vehicle, I want to give a bit of credit to the other people who worked on this. So this is our recent FSCD system description of vehicle, and you have more names here to check out. And in particular, the person who needs mentioning and who wasn't on the picture with vehicle is Bob Atke, who contributed a lot to the design of this language. All credit is given. It's actually not vehicle specifically that I wanted to talk to you today. I will use vehicle as an example of what you can do with neuro-symbolic programming, but not as our main target for the talk. So what is the main target for the talk then? As you have seen from the title, I'm interested to talk to you today about combining proof-carrying code ideas with neuro-symbolic code and get something hybrid. Before I actually go into the details of this, I want to motivate a little bit why would I care about the building blocks in the first place. Well, let's start with neuro-symbolic programs. The truth about them is that they're everywhere. And as an exercise for us all, since we need a morning warm-up, let's convert a standard symbolic program into a neuro-symbolic program in 2 minutes. So what I'm going to start with is a classic example. It's a hello world example in verification of cyber-physical systems. It's due to Boyer, Green, and Moore. As you can see from the citation, if you can read it, it's from 1990. And of course, in 1990, it was purely symbolic. So here's the deal. The vehicle is moving on the x-axis, but Boyer and Moore were not interested in modeling the safety of its behavior on x-axis. They were interested to model safety of its behavior on the y-axis, because the scenario is that the wind is blowing and trying to get the vehicle off the road. So when you see the red margins, these are the safety margins. We definitely want the vehicle to be within those y-axis, those red lines between -3 and 3. what else to say? There's not just wind, the wind also changes. And how does the car deal with the changing wind? It has a controller. In 1990, just a standard controller, no neural nets whatsoever. That controller has access to 2 bits of information: the previous position of the vehicle and the current position on the vehicle on the y-axis. So of course, if you know your previous position on y-axis and your new position on y-axis, from there you can calculate quite a bit. You could calculate your velocity on y-axis, and ultimately this gives you some clue as to how big the wind speed is. All right. So why is it such a hello world example for cyber-physical systems? Because despite its being so small, it already has stochasticity because of the changing wind speed, and some uncertainty because already in 1990 example of Boyer and Moore, they incorporated the possibility that the sensor is a little bit buggy, so it gives you potentially erroneous observations. So if I ask you, how do you convert this into a neuro-symbolic program, even if you're not a specialist in neural networks, you perhaps would have a few ideas. And the easiest one is to say, let's plug out the controller that was there in 1990s and plug in a neural network instead. So neural network will be analyzing previous position and current position and making decisions how to adjust the y position of my vehicle. It's not only just possible to do this, everyone does it anyway, right? So we're starting with the premise that this kind of plugging out of old symbolic code and plugging in of neural networks is happening all the time. And there may be different reasons for this. Maybe my neural network could be more smooth in behavior, maybe it could be more adaptive, less sensitive to noise, or sometimes those symbolic components are just too big to be run on small drones or other devices. All right, so to give us something to think about, let's take Boyer and Moore example and have it in Agda. Of course, Boyer and Moore were not programming in Agda. They were programming in ACL2. It was their own language that they designed for verification of hardware and other interesting things. But why not having it in Agda? It actually doesn't matter in which interactive theory improver you do it. All right, so the state of our system has wind speed, position, velocity, and sensor readings. Observations are wind shift and sensor error. And then you see their controller. For Boyer and Moore, the controller was fully observable, and for us, it's some black box. So we just give a type to it. By the way, we use rationals here, but if you were using, say, ROC with its pretty real numbers, you could also imagine real numbers there. All right. So then you define a state, a next state rather, how you transition from one state to the other. And here, there are only 4 lines for us really to read. And they are actually what you expect, right? So for example, to calculate new wind speed, you need to know current wind speed and add wind shift to it. For new position, you need to know current position plus add velocity plus new wind speed. Remember when you read this, we're always talking about y-axis, so all this velocity, positions, it's all only on y-axis. So it even has a little bit of a flavor of differential equations, which is very standard when you model dynamical systems, because when you start talking about the rate of change, you always have this flavor of your equations looking a little bit like differential equations. So really not that much to say about this piece of code, except for to emphasize that we have modified Boyer and Moore example in these 2 little places. So we plugged out the standard controller, plugged in the neural net, and therefore, in the computation of the new velocity, it is now controller that decides how to adjust my new position. But this is about it. And then you just fold your next state operation over a list of observations, and then you can compute as many next steps as you've given the observations in your list access. All right, so far so good. So what did Boyer and Moore actually do with it? Well, they have the main safety theorem. And the safety theorem says this: if the wind speed never shifts by more than 1 per unit time, and the sensor is never off by more than 0.25, then the car will never leave the road. it is an extremely sensible condition, right? So first of all, you definitely want to guarantee that the car will not leave the road, but on the other hand, you cannot guarantee it for any circumstances. Maybe there is a hurricane and your car is blown off completely. So of course, you have to put the margins and just say, well, it is for this sensor error and for this wind speed that I can give guarantees, and if something very bad happens, well, that's where my guarantees do not stretch. So that's very normal for cyber-physical systems. And that's what they did, and you can reformulate the theorem in Agda for sure, any other prover you like. Crucially, when you try to prove the main theorem by Boyer and Moore, you cannot follow all the steps that Boyer and Moore have taken in their inductive proof, because now you plugged out some of their symbolic parts, so you need to give some guarantees about your neural network. And the guarantees for our neural network come in the form of this lemma, which we called controller safety property. Well, think of it, what you might want your neural network to behave like. It can be arbitrarily fancy and creative, you don't care, but certain things you do care about. In particular, you want to say this: if my sensor and the neural network takes sensor of the position, is actually, the vehicle is now between -3 and 3, so we are kind of within the safety region. Plus, because the sensor is buggy, I'm allowing this to be 325 in both directions. This could be -325 or +325, because who knows, maybe sensor is buggy at this moment. So if it's within this safety region, so I'm still sensing somewhere within the road, so I'm somewhere still there, I want to make sure that the output of the neural network, which gives me adjustment to my position, doesn't get crazy. So you see here the left side of implications exactly tells me that, you know, my sensing is within the safety boundaries that I have, and the output condition that the controller output plus 2 times x minus y should be less than 125. I don't have any good explanation for you. It's just how the differential equations work out to give you the safety property. We had to do a little bit of manual calculation in order to have the second part of implication, though the left-hand side is pretty obvious. So if we do have this lemma, suppose I assume this lemma holds, then Boyer and Moore example goes through in Agda, and Agda is happy, and we're happy. But the question is, of course, is how can we prove the lemma now? Because now the blame is on the lemma. And Agda cannot prove the lemma. This is all black box, so what do I do? And that is the question: how can we enable verification of such neuro-symbolic programs? So I hope that I have persuaded you that it's a sensible question to ask. In a completely different world, in a completely different place, in Popl, 1997, there was something else going on. There's this paper, proof carrying code, that says something completely different. So let's switch gears and think about something else. So the paper starts with this: high-level programming languages are designed and implemented with the assumption of a closed world. In practice, however, programs often have some components written in a different language. All right, and so what does the paper suggest? It suggests to massage down the problem into blocks. So you have a code consumer, that's your safe language. It's already trusted. And you have a code producer. It's a language that you don't trust. So your code producer, the one who you don't trust, produces a safety proof. And then it packages the safety proof into a verification condition and ships that to the language that you trust. And then that proof is validated there in the language that you trust. So that's the whole premise of the proof carrying code idea. In that paper, the actual example that was worked out was this. So the standard ML code was your code consumer, and your code producer that you didn't trust was assembly code. And then the proof search was implemented in ELF on the red side and validated in LF on the green side. Just to give you an idea that it was specifically not about neuro-symbolic programs. It was about something else. And you see verification condition appears second time. So that's what gives name to your vehicle, to the vehicle, to our tool. And you could kind of smell already that something is going on. It almost looks like, oh, you know, you're just plugging together neuro-symbolic programs and proof-carrying code, and I'm done. So for the rest of the talk, I'm actually going to concentrate on how you do it. And of course, I'm going to be based on how we did it in vehicle already. But I really invite you to think how you would do it, because it's not necessarily the only way to have neuro-symbolic code in a proof-carrying mode. However, what I would like to say in my talk is that even if you do it differently, not in vehicle, not in our team, although you're very much invited to join us, you would probably have to deal with these 3 blocks. You will have to have some very good typed verification condition language in order to handle your different interfaces. And then you need to plug it with the ideas of self-certifying code and neural code synthesis. These blocks will become clear as I go, so the rest of my talk will just cover each of these 3 blocks in order. So my thesis is that if it was not us, if it would be you who does proof-carrying neuro-symbolic code, one way or the other, you will have to rediscover those 3 blocks. So I'll try to persuade you that that is the case. So why would we need a good typed verification condition language? Let's look in the abstract. So let's look at neuro-symbolic program abstractly. So you have S, that's your old symbolic program, and you plugged in this neural network inside. All right, and then you have a safety property. That's our big Boyer and Moore theorem as an example. So you have something in mind. You, of course, want to prove that this property holds of your symbolic program and the neural network inside. Usually, if you use machine learning in the first place, you're assuming that there is some hypothesis there to be discovered by the machine learning algorithm. So there is a hypothesis from problem space to result space. Think of this, I know if your autonomous car has a computer vision unit, you're assuming there is such a function that would allow someone to recognize any pedestrian in the world. Yeah. So you're assuming that in principle there is the function that could be approximated. Oh, an important thing to say is that problem space and result space of my hypothetical function are semantically rich. So it could concern velocity, angles, distances. In this case, the semantics is the physical behavior of the system. If it's a pedestrian, also we probably have some kind of notion of a pedestrian in our minds. So one way or the other, this hypothesis that I think exists has problem space and result space that's semantically rich. And then, of course, we want to approximate this using machine learning. So we massage that down further, and we implement embedding and unembedding function, because neural network will only operate on vectors of reals or floats, depending on your implementation. And usually floats by the time you actually implement it. So instead of problem space, now you have input space for your neural network, and instead of result space, you have output space for your neural network. And of course, what happened now is that input and output spaces are semantically meaningless. For example, if I had a semantic of a pedestrian, now this all got reduced to pixelated images 1,000 by 1,000, and that's it. So the semantics of a pedestrian is gone. It's just simply an image of certain size. If I had velocity and angles and distances, they potentially were all normalized between 0 and 1 or -1 and 1. And again, I lost any meaning for that. So that will be important for our verification efforts. And that's one of the big obstacles that we discovered when we just started this project. But one way or the other, once you have input vectors, output vectors as your types, you can train machine learning system F. And I'm using the colors here, red for unsafe, green safe, and orange is kind of a gluing layer between those two worlds. Right, so it turns out that what I actually want to prove is that my property holds of symbolic system and of combination of these functions, embedding and embedding function, and the neural net. Well, Agda couldn't do this either, as you can imagine, and neither would ACL2. So I need to do something about this. How about this as an idea? I will isolate the two parts. And in fact, as far as we have seen my running example, we've already done it. I will first formulate this first property that for every h, if some property q holds of h, then it would guarantee for me that my property p, that is desirable property, holds of the symbolic program and this hypothesis h. And then I will leave an obligation to prove this q separately. That was my lemma that I shown you in my running example. So I'll show this lemma q. It should hold of the system and my neural network with embedded and embedding and embedding functions. Well, that's some progress. That's not too bad. But again, I don't have any tool that would allow me to prove the property double I. So what do? I need to do something further. So I split that even further. Luckily, I have tools that would be able to prove some property of a neural network taken in isolation. And then I just need a middle layer to show that if a neural network is proven to have certain property, then my property Q holds. And then I will be able to go back to my AGDA and ACL2 and finish the proof. Are we good with that? All right. So to wrap it up, the overall proof development for Neuro-Symbolic program will consist of these parts. So I want to prove big property holds of everything. Then I need to find problem space property Q, my lemma, that would allow me to prove the big theorem I have. But then I also need to find input space property R that will hold of my neural network F, and then also prove that this input state property implies my middle layer property Q. So this is essentially what it boils down once you write this up. And our running example has already taken care of stages 1 and 2. So mainly I will concentrate on steps 3, 4, and 5 now. So let's start with neural verifiers. I'm not sure how many people know about neural network verification. So I'll give like a baby tutorial for you so that it makes sense. So a range of neural net verifiers exists. So there is VNN comp competition that is run during CAV every year. And if you're interested to see statistics, what those verifiers are like, please check the competition webpage. I'm just listing few that I know and like. Marabou is based on linear programming and SMT solving. Iran and Prima based on abstract interpretation. This second one, Iran and Prima, is often published in POPL. So if you ever go to POPL, check out. This team tends to be publishing there. VeriSeq based on interval arithmetic, alpha beta crown based on linear bound propagation. Point being that the actual nitty-gritty details of how they implement verification of neural nets differ, but they all somehow work in this manner. They carve out the subspaces of the input space, and then they see what happens with the subspace as you start processing it, taking it through the layers of a neural network. Then they check what happens on the output space, what kind of subspace of the output space gets covered by the time you get your input space shape through the neural net. And then you can make a conclusion whether you got yourself into safe or unsafe subspace of the output space. And the picture is due to Iran and Prima team. But I want to discuss with you a little bit how this is actually done, because I think it's interesting and it will be important for us later on. So I'll concentrate on reluplex algorithm that was introduced by Kai Katz and that underlies the Marabou verifier for neural networks. Reluplex algorithm is based on simplex decision procedure known in linear programming, and it specifically works for linear real arithmetic, because that's what you need for neural nets. So let's have a look at this example of a tiny neural network. You can see it there on the right. And I'm specifying some verification condition for it. I'm saying, well, how about this? Can you prove for me whether this is SAT or unsat? If inputs to these neural networks are between 0 and 1, I want to ensure that the output is between 4 and 5. Now, it's a slightly different example to what we saw in the Boyer and Moore. reformulation, but it has the same feeling, like I'm putting some boundaries on the inputs and I'm checking whether certain boundaries on the outputs hold. This is iconic for neural net verification. This is a sort of guarantees that neural net verifiers give you. All right, just a reminder for those who have never seen neural network or see neural net definition and forget it every time they see it. So there are a couple of very simple functions going on inside of the layers of neural networks. So first of all, given some signals, some inputs from x1 and x2, for v1 and v2, we compute the weighted sum of their inputs. So for example, the inner sum for v1 is 2x1 plus x2 because the weights are 2 and 1. And once you compute those inner sums, you also apply a ReLU function on top. ReLU function simply gives you 0 for all the negative inputs and gives you identity function for all the positive inputs. And that's really all there is if you wanted to define a neural net. All right. So the duplex algorithm goes in this way. It says, well, let's say we have a variable vector and put all those key components of a neural network as a variable. All right, so x1, x2, inner sums, results of inner sums of those. Then v1 and v2 are the results of applying ReLU to in1 and in2. Let's not worry about aux1 and 2. And then there is y for the output of the neural network. The bounds, initial bounds, are given to us by the verification condition that we have. So we may just ask how to propagate those bounds. So assuming in1 and in2 are the weighted sum, clearly that the fact that x and 1 are between 0 and 1 already determine for me the boundaries for in1 and in2, right? I simply propagate the weighted sums through it. So let's have a look, for example, how number 3 is computed. So 3 and 0 as lower and upper bounds. So that is in 1. So we look at v1. You can see that x1 and x2 maximum can be 1. So the maximum of their sum would be, bear in mind that their weights are 1 and 2, will be 1 plus 2, 3. So that gives me the upper bound for in 1. And what will be the minimum of their sum? Well, if x1 and x2 as their minimum are 0, then the minimum of their sum will be also 0. And you can imagine, you can keep on propagating. For example, next time I propagate the bounds, I apply ReLU. So ReLU does identity on positive inputs, and it converts -1 into 0, because all the negative inputs, it converts to 0 by definition. And then you continue. OK, so then you have this variable vector, and you have your lower and upper bounds. And what you need to find out is whether it's in some sense consistent, because 5 and 4, I just put them by definition of my verification condition. I need to actually check that this gives me a consistent problem, right? Because who knows, maybe 5 and 4 were arbitrarily chosen. They're not obtained by propagation of the bound. OK, then the duplex algorithm proceeds by massaging down definitions of these neural networks, or rather functions of these networks, into equations. For example, if you have a look at the first one, it says that 2x1 plus x2 minus in1 equals 0, where it's similar to saying that in1 equals 2x plus x2, and so on. So for every neuron in your neural network, you generate an equation. And then you may also wrap up these equations into a tableau, an array of numbers, but in formulation of the algorithm, it's always called tableau. So for example, the very first line, you could see the coefficients for x1, x2, and in as per the equation number 1. So there is a lot of nitty-gritty stuff going on there. This is all a preparation for applying a Farkas lemma in checking that this all makes sense. So the duplex algorithm will go and try to find an assignment for my variable vector x, such that that variable vector, that vector v, is between lower and upper bounds on the one hand, and then if you multiply, take a dot product between a and v, you get a 0. So if that happens, it means your v is a solution to the problem. If the algorithm fails to find such a v, it will report that there is no solution that exists. So this mode of computation is very similar to SMT solving, yeah, to any SAT-unsat problem. Either you find an assignment that satisfies certain condition, or you report that none exists. So the procedure is sound and complete. Okay, so this is just to give you a little bit of a flavor of what's going on. We did not implement Marabou. We only helped to eliminate some bugs in Marabou, but otherwise this already existed when we started to work on vehicle. Well, wonderful. That's great. The technology exists, we can use it, why not? So how about then embedding proofs? Suppose Marabou works for us and it gives us an output. How do we embed this back? And this is where vehicle comes into play. So vehicle is a specification language. You state neural network properties in vehicle. And the first thing that you want to do is to send it to Marabou to have this neural net verification. It is shown, the stuff that I've shown you, duplex algorithm and execution of it, is shown as a devil here. But really it's just as an algorithm as any other. It's simply that we cannot fully trust Marabou. It's quite a big implementation. But otherwise, why not? We run the Marabou. We get certain guarantee from Marabou that the property holds. We lift it back to the specification language and pass it back to Agda, Rock, Isabel, Hall, to whichever prover you want. Agda was the initial interface we implemented. Rock has been implemented this summer, and Isabel Hall work is underway. So that's the idea. Let's have a look how it works. So this is now vehicle, finally. So that is the Haskell DSL, so it looks a little bit like Haskell. So this is our middle layer between low-level crunching of vectors and arrays in Marabou and very high-order reasoning on the Boyer and Moore example, or in any example you want to program in your interactive theorem prover. So let's have a look what vehicle does. It's a hopefully no-nonsense language, because we were hoping that actually practitioners who verify neuro-symbolic programs will use it, not necessarily functional programmers. It has dependent types, but it doesn't have induction or recursion. So naturally, and this is a vehicle property for Boyer and Moore example, naturally it goes and specifies inputs and outputs of neural network. Remember, my neural network takes two inputs, previous and current position of my car, and gives one output how to adjust my position, or rather my y velocity. So therefore input is given by tensor of reals of size 2, output is given by tensor of reals of size 1. The neural network here is not defined. It lives somewhere else in a different file, but we give its type. The type of the neural network, which is called controller here, is from input to output. If there is any normalization procedure that used to be hidden under the carpet before, we must declare it here. It's this embedding function that we were discussing. In this case, we don't use any unembedding function. It's only the embedding function that we declare. And then I define safe input and safe output, just as I told you 10, 15 minutes ago. So this is just vehicle's representation of boundaries on two inputs and on an output. And then the main controller safety property, that's the lemma that we have finished with our example with Boyer and Moore, says that you must guarantee for me that safe input guarantees safe output. Okay. And this is all. So this is all we need in order to specify this middle layer property for Boyer and Moore example. What do we do with it? Well, let's run vehicle. If you scan this QR code, you could get yourself to a tutorial. It's very easy to install both vehicle and Marabou. You just have a pip install command on the tutorial page. It's installed. You need to have VCL specification that we've just seen on the previous slide. And you need to have your neural network in ONNX format. It's a format that is used by neural net verification community to verify neural nets, so we just kept it there. Then you have a command line in your terminal, vehicle verify. You say which specification, it's the wind controller, which verifier Marabou, and you give a path to your neural network. And after just a very few seconds, vehicle will tell you that it's safe. It says, hey, Marabou has proven that there is no counterexample for this property. Hooray, you're done. Okay, so let's just stop and think what has just happened. Underneath this execution, at least two things happened. First, vehicle computed the property R, because we didn't give it a property of a neural network. We gave it a property of the lemma we want, so that the more and more example goes through. So it actually computed this R for us, the suitable neural network property. And then it has proven that neural network property implies the orange, the middle layer property. So how did that happen? So first of all, let's have a look how it computed this R. As you can see there, it says verifying property safe, 2 out of 2 queries. And if you're like, okay, what are those queries? If you actually go down the files and see what vehicle generated, you will see that these are the 2 queries, and this is the format VNN lib that is used by neural network solvers. You may be from that community or from functional programming community, but I'm asking you, would you like to write properties of anything in a language like this? This is the whole file. It doesn't say what the types of X and Y's are, where they come from, what it is. No one knows. It's just, this is the whole file of specification for a neural network property. Should any human write properties of neural networks in this way? I don't think any human being should. And before we implemented vehicle, that's how human beings were writing neural network verification properties in this language. It's a VNN lib standard. So it might be good for a compiler, but you certainly don't want to specify properties for systems in this language. So we have it hidden. Hopefully the user of vehicle would not see it. This is something that Marabou crunches once it starts working on this. All right. And how about proving that this strange Marabou property implies my lemma? Well, there is a type checking mechanism in vehicle. So first, after scoping, it does the type checking. It will normalize and generate the queries to Marabou, just as we've seen. There are other things that this type checker does. It will have for us checks for linearity errors and quantifier errors. Why is that? Because vehicle is high order language. It has dependent types. It's much richer than the language of VNN lib to which you compile. So it's very possible that you specified something in vehicle that Marabou cannot crunch for you. And this check will flag for you if you have specified a property that's outside of the fragment, decidable fragment of what Marabou can do. In particular, Marabou expects linear properties and a very specific quantifier nesting. All right, so thanks to the type checking, to the type system, we have the guarantee that that low-level property of neural network that I have guarantees for me the middle layer property of the system, and that is very nice. This is something that we really need. All right, so let's just wrap it up. Let's finish more and more example. We have just gotten proof of this lemma from Marabou, well, through this middle layer specification language. And how about finishing this? By another command line, vehicle generates for you an Agda file automatically that is simply a translation of the specification that we've done in vehicle into Agda. So this will be a separate Agda file that you can use in the proof of your main theorem. It looks a little bit dirty, a little bit ugly, because it's automatically generated Agda rather than human-written Agda. But otherwise, this is the file that you're going to be using to finish off your main theorem. And so in this type checking system, you add yet another leg. You now compile this all to ITP code through another pass to your type checker. And as I said in the moment, we have Agda Rock and interfaces working, and Isabel Hall is going to be ready very soon. But point being is, once you have this bool set type check implemented, adding more and more interactive theorem provers is actually becoming a mere engineering task. It's not that difficult. You're still reusing the same typing procedure for all of them. So that's nice. So to sum up what just happened, we have just noticed that in verification of neuro-symbolic programs, we have an embedding gap between the problem space that is nice and safe and has our interactive theorem provers and our nice specification language. And then there is this embedding space that talks about vectors and kind of somewhat untrusted, at least notionally. And so we have just implemented a compilation procedure from specification language vehicle to the verification languages such as Marabou, and build the embedding gap, bridge the embedding gap. So that is as much as one needs to know about the vehicle. So it handles the embedding gap safely, builds SMT backend in the form of Marabou, and type system generates and handles complex constraints consistently. So that's all nice. I will very briefly tell you about two other quirks that happen in implementation of this language. And let's start once again with Necula's idea. The thing is, when he was suggesting this in 1997, if we think about how this whole idea fails, and I'm having a table there calling symbolic PCC I'm using that word to refer to Necula's example. The incidence of code that fails verification condition assumed to be low, right? Okay, he was saying assembly code is very unsafe, but he was assuming that basically there is a bug once in a while, but it's not like it's totally unsafe all the time. So first of all, the incidence of code that fails verification condition was low, but if it did happen, the assumption was that it was amenable to manual repair. So if an error in assembly code was found, then someone would be able to go and actually fix it. And what happens in neural network case, in Neuro-Symbolic case, is that if we have our vehicle implemented and so on, and just run it, well, in some cases, up to 96% of cases come back to you and say, it's not verified, sorry, this specification that you've given is not valid for this neural network. And then what do? You cannot just go back and manually fix the neural net. So, of course, the idea is to somehow get to fix the neural network without doing it manually, because there is just, it's going to be your routine. If 96% of cases you fail, then fixing a neural network should become automatic for you. It cannot be done on an ad hoc basis. Well, thankfully, machine learning people have thought about this long ago. So it's a very popular topic in machine learning. You can optimize machine learning models for a property by generating new data, new loss functions, and some other parameters. I'm just last night looked up any new paper in 2025 that I like on this topic and provided as a citation. But literally at any point you can go and check what's the new paper on property-driven training, and you'll find something. There's abundance of stuff in there. But the one that we picked up was based on generation of new loss functions. And I'll give you just a very quick example, because I don't want to give you anything in machine learning terminology. Suppose I have a toy language to write my verification conditions, and it only has comparisons between x and y's and a conjunction. Well, I can define a translation for each of my expressions in the language. And for example, I'm going to be saying that x1 is less than x2. I'm going to be interpreting as subtraction. Why is that? Because if x1 is actually smaller than x2, then the result of subtraction will give me a negative value. It means the penalty for a neural network will be negative, so there is no penalty. But if x1 is greater than x2, the value will be positive. It means the neural network will be penalized with the actual value. The penalty will be substantial. And then suppose I wrap conjunction as multiplication. And then you can use the resulting function as loss function to optimize the model. And to persuade you that it kind of works, I just put an example here that we used to show you how the duplex algorithm works. Remember the one when we had 0 and 1 boundaries for input and 4, 5 boundary for output? You could put it through this translation and can get some crazy function that is, again, pretty meaningless. And once again, probably you don't want a human being to write anything like this, because the meaning is somewhat lost. But you can use this yellow loss function in order to optimize your neural network to satisfy the property that you want. Luckily, I don't need to say much here because vehicle has already infrastructure to handle for us the dirty world of machine learning. So we get here a result for free, essentially. You see that there is some empty bit in the square. So of course, I'm going to fill it in, if I may. So if I can generate loss functions from specifications, and I can, I simply plug this in inside of my compiler. Since I have property Q written in vehicle, I may just say, please, vehicle, could you generate for me these loss functions, pass it over to this red world, do the training with this specification property R. If verification for R fails repeatedly, could you have this loop several times, train it until the property is actually satisfied? And actually, I don't want to see it in my green world. Just do it at your own leisure. The only thing I really care about is that my compiler handles compilation from specification language into a loss function, and the rest happens on its own. So that was for free. What wasn't for free? We spent quite a bit of time proving properties of these loss functions, because for machine learning people, it's not a problem. They could do whatever they liked. But if you actually want this to be part of your compiler, you probably want to prove something about these differentiable logics and loss functions. So we've proven some soundness properties and some properties that are pertaining to training, like smoothness and monotonic increasing for or decreasing properties for conjunctions, junctions. And so that was published in ITP last year. All right, so we have extended our picture somewhat. Now vehicle has 3 interfaces: to verification, training, and finally integration with the provers. So here you are. All that we needed to do is to have another type checking pass into differentiable type checking part of our system that will generate loss functions, and then TensorFlow will take care of the rest. So in neural code synthesis was almost trivial. So loss function synthesis via differentiable logics, that is fully done, and TensorFlow full program synthesis from vehicle is in progress. So we don't actually have this backend fully working yet in TensorFlow because it required quite a bit of engineering to do composition of all these loss functions if you have big specifications. But basically it's engineering work rather than a rocket science at this stage. All right, and very quick note on self-certifying code. There is a third important building block. Going back to Necula, in his case, he could actually, because his proofs produced by the code producer were written in ELF, and then he needed to validate them in LF. The gap between these two languages of the initial proof that was found by the unsafe side and the safe one was extremely small. Quite easy to convert one proof into another. And in our case, Marabou proofs through reluplex are so different from the proofs you have in Agda. So we needed to think a little bit about this. Luckily, there is something that's called self-certifying code tradition. And if you've never heard of self-certifying code, I'm providing the citation to Communications of ACM this year, which has a very nice overview of different approaches to self-certifying code. But going back to the problem in question, verification of SMT solvers, forget about Marabou and neural network verifiers. Verification of SMT solvers is a no-go. They're too big. No one has ever verified a whole implementation of an SMT solver. And similar would be with Marabou. Not for a single moment we consider taking a Marabou and verifying it like in a comp-cert manner. But what is a nice solution for SMT solvers is to generate a trace of execution of an SMT solver. And then have it, you can actually even render it as a proof term in your interactive theorem prover. And this is a path that CVC5 has taken, and now it can actually render those proof terms into lean. So this has been done in SMT solving and interactive theorem proving community. Clearly, one could consider that the same thing could be done with Marabou and vehicle. So what's the deal? The team of Amri Isaac, Clark Barrett, and Guy Katz already thought about this, and they have published a paper in FMCAT 2022, where they basically conveyed this information. If you have a neural network, you have your specification, and you have your verifier, in their case, Marabou. Then if an instance, if this vector V is found, that's your counterexample, and you can immediately check it. So that's not a worry. The problem is that even you have a case unsat, the case unsat basically says, I couldn't find any example. Well, that was very difficult to certify. And their idea was that, well, we could produce these certificates during the execution of Marabou and then have an independent checker to check those certificates. How did they do this? Apparently, there is a Farkas lemma, very famous in computer algebra and linear programming, that gives you certain guarantees on SAT and unsat of linear programming problems. So if you have A, X, L, and U, as per my previous example, exactly one of the options holds. Either you're in the SAT case, so you could find a vector V that both is between your upper and lower bound and gives you dot product with A equals 0, or you are in unsat case. So SAT case we have considered in good detail within this talk. But there is also unsat case to the Farkas lemma that says that if it's unsat, there actually exists a contradiction vector, so that if you, for any x that is between your lower and upper bound, you multiply the contradiction vector by A and X, and when I say multiply, it's all dot products, then the result will be less than 0. So the Marabou team, of course, had this big idea. They said, why don't we have a constructive Farkas lemma for Marabou, and that will be our way to generate those certificates. So the contradiction vector W can actually be constructed during the execution of Marabou. The idea there, on top of the fact that you use Farkas lemma, is that Marabou has, and Relu-Plex algorithm generally, gives rise to some sort of a tree structure because of processing of ReLU nodes. So it searches for LP assignment, either it's find contradiction, or then it starts going inside of the ReLU nodes, then starts checking piecewise linear constraints, which are ReLUs given by ReLUs, and then either it finds a counterexample or splits into subqueries and repeats. So if you were to visualize the whole proof search in Marabou, it will be like a big tree. For our tiny example, though, because there are only 2 ReLU nodes, there will be only 2 splits. And in particular, so for our example, this is how Relu-Plex search would look like. It's a ReLU split on the node V2. The details are not so important here. The point being is when you finished the search, when your proof tree is there, in each leaf of that tree, you could have a contradiction vector computed during the execution of Relu-Plex. So that was important for the Marabou team. And then if you do assemble those contradiction vectors at the leaves, you can just plug it inside the Farkas lemma and simply check whether these contradiction vectors satisfy the Farkas lemma, and you're done in terms of certificates for your unsat. Well, it's quite a mouthful. So obviously, when they presented this at FMCAT 2022, the obvious criticism to this, can we actually be sure that this is all correct? Because it's a little bit hacky, something happens with vectors, contradiction vectors. If you wanted to put this inside of a compiler, you have a little bit of a job to actually prove that this all gives you something valid, even the theory is nice. In terms of programming this stuff, it actually requires quite a bit of work. So in proof-carrying code, we need to formalize and prove the constructive Farkas lemma in entrusted theorem prover, and then use this formalization in independent certification of Marabou proof trees. So this took us quite a while. It was published in ITP this year. So finally we have this certified proof checker, and it was implemented in Mandra because PhD studentship was funded by Mandra. But it could be done in another interactive theorem prover as easily. So to summarize, we have formalized constructive Farkas lemma for Relu-Plex. and implemented independent certification checking. There is quite some work to be done on doing these proof certificates compositionally in vehicle and perhaps even generating safe neural networks from certificates. So it's not fully done, but a big chunk of work is done. So to conclude, proof-carrying neuro-symbolic code broadly follows the principles of proof-carrying code. But there were 3 quirks, and I think anyone who would do this again or would be compelled to do this again is bound to rediscover these 3 things. So first of all, you need a very good verification condition language that will help you to bridge the embedding gap between neural and symbolic domains. And types are ideal to keep you right there because there are just so many backends and you want to have some source of truth. You would probably have to again rediscover synthesis and repair of neural components using quantitative logic, simply because not every time that you try to verify something, you'll actually be able to do it. And finally, you will need to sort out the question of self-certifying code, because it's not enough to just say Marabou has proven it and I don't want to see it. You probably want to leave those certificates back to your high-order language, so that's important. So the important message is on this slide, and it's like, rejoice. Not only you can do it, but actually programming language and types technology of the day allowed us to do it almost for free. When we were with our team discussing whether to submit vehicle to ICFP or POPL, there was always opposition within the team to submit it to ICFP and POPL, because the argument was that it doesn't actually contribute anything new to programming language design, which for us may be a bad news. But it's wonderful news for programming languages. It means that in 2020, when we started this project, the technology with types, theory improvers, functional languages was so high that such a complex project could be achieved essentially at no additional theoretical cost. So this is a big news I wanted you to know about. It's so congratulations to this community for this. And I wanted to finish with just quick postscriptum. Because you would say, well, this is so cute, there's vehicle and robot Isaac, and everything has nice interfaces, but what's the catch? I mean, how real this whole thing is? So we probably need to discuss large and small language models. The catch is this. So the technology on which vehicle was relying and our proofs were relying was verification of neural networks. And really, neural net verification is proven to be NP complete. So this is bad news, of course. Still, nonetheless, and same with SMT solvers, some of them are NP complete, and yet people do improve their performance. Similar situation happened with neural net verifiers. Since 2017, neural net verifiers saw speed up to annual rate of about 1 order of magnitude on the size of network. So they were speeding up significantly in the last few years. So that's good news. So how big then? Oops, sorry. In 2025, VNN Comp featured models up to 68 million parameters. So the neural networks that I was showing you was, what, 5 parameters, yeah? And 68 million is what you can have, like if you just download the verification tools of today. Versions of these same tools developed by companies are reported to be able to handle about 350 million parameters. But if we look at machine learning world and look at this graph, we'd be able to see the growth of real machine learning models, models employed by big players. And we can see that in the last few years, they have grown to billions and even trillions parameters, yeah? So this is way above the best neural net verifier that we have on the market today. So that's, again, bad news. But there is good news again, and this is an important catch. At the same time as models were growing, as something else was happening, if you were just given a task, like recognize cats or pedestrians, or implement a controller, then progressively over time, you need models of smaller and smaller size to do this. And this actually gives hope for neural net verification, because this red box is now the models which are easily within reach of neural net verifiers. So realistic scenarios for verified neuro-symbolic code are controllers in autonomous cyber-physical systems, because they are rarely bigger than 68 million parameters. And small language models, which are apparently on the rise. The talk is, and I'm citing here The Economist, that more and more producers will be focusing on small language models defined as models up to 4 billion parameters. The idea is, if you want to generate your AGDA proofs, you don't need the same large language model to know how to bake cakes. So you can isolate those models and have them small. And some of the big players on the market actually are recognizing this very fine line between what neural net verifiers can do and how small the models should become in order to be verifiable. So that's a new DARPA Assured Autonomy mission. If you actually look at their tools page, you will see majority of investment has gone exactly into neural net verification. And I think this is in recognition of the trend that some models are becoming increasingly smaller, and you will be able to verify it. So the future is, it is of course still early-ish days for neural net verification, but when tools like Marabou and its successors mature, they will need to be safely integrated into trusted code and trusted verification pipelines. And for this agenda to succeed, of course, neuro-symbolic code must meet proof-carrying code. There's just no way you'll be able to trust all those big verifiers without repeating the same steps that I have just shown you. And finally, functional programming and types communities have this unique expertise to make this happen. So, in my opinion, future safety of complex systems with neural components is actually a programming language challenge, because neural net verification challenge is almost there, it's almost resolved. And the next step will be people to learn to do what we have discovered with vehicle, faster, better, perhaps more elegantly than we did, because that will be really the biggest catch for safety of AI. Thank you.
Oh yeah, good, it's on. You talked about progress in the size of the model network you can verify. How much of that is just Moore's law versus how much is actually algorithmic improvement?
I'm not sure I understand your question.
Okay, you said every year we get roughly an order of magnitude increase in size in that one. Is it just because our computers are getting faster?
Oh,
or
yes.
do we know how much is actual algorithmic progress?
Yeah, there are heuristics and optimization techniques there. So the plain reluplex algorithm that I have shown you is awfully inefficient. And so you could implement lots of heuristics, say never explore that ReLU branch at 0 anyway, cut down that search space. It's mainly that. And of course, just improvement in computing power, but mainly heuristics.
Thanks.
So over here. So for the neural network verification bit, as I understand it, you give to Marabou or some other system a property that you'd like it to prove for a particular set of 4 billion weights.
Yes.
And then it says, yes, the property is proved, and maybe here's a certificate that you can check.
Yeah.
Okay, but then I do a little bit more training, and now, a different 4 billion weights emerging. I have to run verification all over again. That's question one. And question two is, and what if it says, oh, very sorry, I can't verify it. Might be true, but I can't verify it. Then, you seem to be a bit stuck. Shall I train it again and just hope for the best and keep, do you see, how can you guide it towards something that is verifiable?
Yes, so all you've said is exactly true.
Okay. So
the assumption is we do not have any notion of a good neural network. Like all of them are equal to us as long as they satisfy the verification property and are good in optimization terms as well. So yes, we're happy to retrain as many steps as we need. And then once it's a tick, we just take that precious neural network and deploy it in our autonomous system. So the earlier part of my talk was about using specifically guiding through your compiler towards property satisfaction. So this was this bit. It's probably worth. So you can use the same vehicle compiler to generate loss functions so that you guide your neural network to satisfy the property through training. But it is not a guarantee, so it may never converge to satisfying your property whatsoever. And in that case, you just say, well, I failed. But in majority of cases, it's very efficient. So you start with, oh, this property is not satisfied, and after some training and twiddling, you make sure that it does satisfy the property. It turns out to be surprisingly easy.
Okay, that is surprising, yeah.
But we were not dealing with large language models or something like this. These were neural networks of small sizes with very well-defined properties.
And if you have 4 billion parameters, then the certificate of its validity is also
huge.
Size 4 billion.
It will be very
so there's
huge,
quite a lot of
yes.
checking to do.
Yeah,
okay.
It's a lot of checking to do. But it's smaller than looking for those certificates. Yeah, it's the same case with SMT solvers. Finding a certificate is hard. Checking it is still much, much easier. But it's quite big nonetheless. You're right.
I'm going to ask my question by way of a concrete example because I think that's easier. Like, let's suppose that you're applying this to like some image recognition thing, right? So then your model is like your 3D world, and you can easily write a projection of that into some 2D space, which is what a camera would see, and you build a neural network on trying to recognize things in that 2D projection. Okay, so then if I understand this right, the projection of a 3D world into a 2D thing would live in E, I guess. But then, like, the reason we use a neural network for a problem like image recognition is that because we have absolutely no idea how to do that symbolically, right? Yeah. So I can easily write something that renders a rabbit from a certain angle, and then, but we don't know how to do it. But then, wouldn't you have the exact same problem when trying to write Q or P, because you would need to formulate it in terms of the 2D image of a rabbit? Because, you see what I mean? Like,
yes, yeah, it's called the problem of a missing spec. So for large language models and computer vision models, there is a problem. So how do you define pedestrian in pixels? How do you define a cat in pixels? If you cannot do this, this whole technology could go to the bin because our specification Q will be missing and we're done. There is no solution to this problem. That's why all examples, no good solution, no general solution. All examples I was using were controllers where the property Q is very well defined. There will be domains where you use neural networks specifically because you don't have a property Q. And unless you can conjure it or somehow massage it, you will not be able to apply this technology. So this is a serious limitation. So actually I cheated. I told you scalability is the only challenge. The second one is the missing spec. This limits the number of applications you can have for this.
Okay. Thanks, Katya. That was a really nice talk. I like the way you put all the different technologies together and told us we were actually doing the right thing. But the only example you talked about was the Boyer-Moore example of a car with a little bit of wind not being pushed off the road. But where I really want to know is the Waymo or the Tesla is not going to kill anybody. I want to know for my large language model that's not going to advise teenagers to commit suicide. So what sort of things realistic? You didn't talk very much about what interesting safety properties we might actually be able to prove. Could you give some examples?
Yeah, so I think that's why in postscriptum I referred you all to the stool webpage of the new mission of DARPA. So my understanding is that for these to be funded and funded at a large scale, you will make the argument that I've given to you, that autonomous systems with these controllers where you have good properties, there is no reason why you shouldn't be verifying them routinely, right? So if I can verify Boyer-Moore examples and the likes at a large scale, I must be able to do it. And there was not even technology to do it. We had to write vehicle in order to handle the whole thing.
Right, but okay, now I've written vehicle. What is a property of my car or whatever that I could actually verify that would be a useful safety property?
Yeah, so these will be some boundary conditions on performance of your controllers, for example. So in that sense, more and more example is exactly the indicative of what you will be able to do. So your system has some small neural net component with well-defined properties of that component, and then you verify it. It's very similar to the previous example. So if you were thinking that we'd be able to verify the computer vision unit in Tesla, we would not.
So it's something like the robot arm will not go beyond a particular bound when I'm doing automated manufacturing.
Yeah, and then if the robot arm does not go in that particular direction, then you would not hit the wall. So you take the guarantee on the neural net and then propagate it through all of your program, because if nothing bad happens with the neural net, nothing will happen with the rest of your program. That was the idea behind more and more example. Yeah, I could guarantee a complex behavior of the system if I could say that I have certain conditions on this controller. The example of Boyer-Moore is not as silly as you might think, because I still allowing quite a lot of flexibility for that neural network. I only limit it on some safety conditions. It could be arbitrarily creative and it's just here what two inputs, but there are other examples when you have controllers with many more parameters, and neural networks behave better than handwritten controllers because they give you solutions that a human programmer did not come up with. So my verification condition Q only limits some safe, unsafe kind of behavior. So that is the game there, but not verification of some like computer vision units, mainly because there is a missing spec for those. So it's not the problem of vehicle, it's the problem of machine learning, if you like. Yeah, if you don't have a specification, if you don't have a property, you're done.
Right. Okay, thanks.
Hello? I was curious if this is going to be included in things like autonomous systems like a robot or a car. Have you ever verified the actual, like, I guess, runtime characteristics of how long it would take for the neural network to run? So inclusion in, like, I guess, a real-time operating system? Because presumably if it's like, let's say a robot arm, if it needs to act within a certain amount of time, would you be able to prove properties like that about the neural nets?
You mean, will you be able to run verification real time as you drive your car?
Yeah.
You probably don't want to do it. For small neural networks, it's very quick, but the idea here is that you verify this neural network, give certificate, and then you deploy it with certificate attached.
Okay.
So that's my understanding is how it's going to proceed.
Yeah.
Okay. Oh, great. Hi, Jeremy. This is maybe going back a little ways, and I'm sorry if I just didn't follow, but the sort of reduction from your property Q to P to R, I think I didn't quite follow how you're able to generate the R that doesn't care about the embedding and unembedding at all.
Right. Well, there is a very simple type system running underneath, and there is normalization of all your. For example, in my example, there was a normalization function, so it will go and normalize, and it will work out this property R just from the property Q, basically by normalization. There's a simple type system that also checks linearity and quantify errors, but it's as simple as normalizing the stuff, basically.
Got it. Are there problems where those embedding and unembedding functions become more gnarly in some sense, or are they always relatively straightforward?
Straightforward unless your property Q is not satisfying the linearity and quantify fragment.
Okay, got it. Thank you.
Thank you. That was really incredible talk. I was wondering about neural networks that are built with non-ReLU based activation functions. Like, what if it's something really like a bit more complex, like a hyperbolic tangent or something like that? Has there been work to handle that kind of thing?
There is indeed. I totally ignored it because the only way we could construct certificates was for neural networks. But in this neural net verification competition, there are tools that work with nonlinear functions. My guess is that it will be harder to get certificates and prove validity of what they do, but they do. There is plenty of work in it. Mm-hmm.
Wow, great, awesome, thanks.
One more?
No.
Okay. That's actually related to that one. So actual neural networks, they work with basically bits with very finite precision, but your verification seems to rely on having rational numbers. How does it interact?
Well, not exactly. So vehicle has reals. So I'm citing here this paper. The trouble with floating points, reals, infinite precision reals, and then integer representations of neural networks is a huge one, and it's partially discussed in this paper. I ignore this for now. So vehicle type system as of now has reals. The Agda example used rationals. Ideally, we haven't had time to do this, but ideally you want part of this infrastructure that I represented to also take care of some of the number conversions. But actually, it's one of the reasons that some of the current neural net verifiers were shown unsafe. It's because in specification you specified it in reals, then the real neural network, actual real neural network is with floats, and then you get some discrepancy between this, and then your certificate is invalid. So you absolutely hit the nail on the head. If you like, that's a third challenge that exists there, is also with numerical conversions. An easy hack, if you wanted to, would be to quantize all your neural networks and do all in some quantized version so that you avoid the problem of reals floats altogether. But this is, I guess, then not a programming language challenge, but there are some interesting things to resolve with numerical representations.
Thanks.
Okay, let's thank Katja again. And it's time for coffee.